Hi everyone, welcome to our channel. Today, we will be learning about one of the most confusing but also one of the most powerful topics in C programming. Pointers. For many beginners, pointers look like magic symbols. You see a star, an ant, some strange memory address, and everything suddenly looks scary. But here is the truth. Pointers are not magic, they are just address in memory. Once you understand what's really going on under the hood, you will realize that pointers are simple and they make it extremely powerful. And don't worry, in this video, we are not going to force you to memorize all of the syntax. We are going to visualize how pointers work step by step and see what happens inside memory when we run our code and you finally understand it. Let's go.
Let's take a look at today's outline. On the left side, we can see what we're going to cover. First, what is a pointer? Then we'll go through syntax, followed by the operators, that's reference and dereference. And of course, some examples to make everything clearer. So this will be a roadmap for understanding pointers step by step. Now, before we're talking about syntax or symbols, let's answer the question. What exactly is a pointer? Let's start with a simple mental model. Imagine your computer's memory as a giant neighborhood full of houses or boxes. Each house can hold something inside, like a number or a letter. When you write in x equals 10, you're basically saying, "Hey computer, please find me one empty house, label as its x, and put the number 10 inside." Now that house also has an address. Maybe it's something like 1002 or 0x7ffeeabc. It's a unique location of that box inside memory. When the program runs, every variable you create, integers, floats, characters, they all live somewhere in that neighborhood, and the compiler keeps track of which house belongs to which variable. So in a way, your variable's name is like a nickname, but the real location of the data is its memory address.
Now, imagine that you don't want to store the number 10 directly, but instead, you want to keep a note that says, "Hey, the box that holds 10 is over there." That note is what we call a pointer. So, a pointer doesn't hold a value like 10. It holds the address of another variable. It's like a map that says, "Go to this location to find the value." This idea might sound simple, but it's extremely powerful because now, if we know the address, we can find and even change the value inside that box.
Now, let's talk about two very important syntax in C programming, the asterisk and the ampersand. The asterisk symbol means contents of or value at. When we place asterisk in front of a pointer, it lets us look inside the address that the pointer is holding and see the actual value stored there. The ampersand symbol means address of. It lets us get the memory address of any variable. For example, if we write ampersand x, it means the address of x. So in short, asterisk let us look into an address, ampersand let us guess an address. In C programming, we use ampersand to retrieve a variable address. That address can be stored inside a pointer variable, written as type pointer name. Then we use asterisk to access the value at the memory location.
Now, let's take a closer look at what actually happens in memories when we assign those pointers. First, look at the integers variable id. It stores the number 10 and we can see it occupies its own memory address. Let's say 1000. That means inside this memory box, the value 10 is saved and labeled as id. Think of it like a small house named id with number thousands on the door. Next, we have a character variable c is store the letter k. Both are normal variables that store actual values. Now things gets interesting. We also declare two pointers variables, ia and ca. Remember, pointers don't store values like 10 or k. Instead, they store address. They remember where something lives. So when we write ia equal ampersand I, ca equal ampersand c, we saying, hey pointers ia, your job is to keep track on where I lives, and hey pointer ca, you keep track on where c lives. In the memory table, we can see that ia now holds the value thousands, which is the address of I, and ca hold the value 1002, the address of c. So the pointers aren't holding the data directly. They're holding the directions to where the data is stored. In simple terms, I store 10, c store k, ia store the address of I, ca store the address of c. That means main concept behind pointers variable. They don't hold values. They point to where values are located in memories. But before we go on, let's look at some of the most important concepts, dereference and reference. What does it mean? Reference means taking the address of an access variable using the ampersand operator to set a pointers variable. From this example, P1 stores the address of C1 to be valid. A pointer must be set to the address of variable of the same type as the pointer. Otherwise, the behavior is undefined. Dereference, on the other hand, means using the address operator to retrieve the values stored at the address that a pointer points to. For example, this means we take the value stored at the memory's address inside P1 and assign it to N1. In this case, N1 will receive the value 5 because P1 points to C1 and C1 is 5. It's important to remember that the values received stored, the reference must be of the same type as the variable the pointers point to. Is this only guaranteed if the pointers was correctly assigned?
Before we move on to the pointers, let's look at how functions normally pass data in C. This is called pass data by value. That means when we send a variable into a function, the program makes a copy of that variable's value. The functions only work with that copy, not the original one. So any change inside the function won't affect the original variable in main. Let's see how that looks in code. Here, a simple example that calculates the average of two integers. In the main functions, we declare two integers x equal 2 and y equal 4. And then we call the function ans equal average x and y. Notice that we are passing values, not addresses. So only the numbers 2 and 4 are copied and sent into a function. Inside the function average in A, in B, two new variables A and B are created in a separate memory area. They receive copies of x and y, so A is equal to 2 and B equals to 4. Then on line 5, a new variable avg is declared to store the result, it calculates a plus b divided by 2, which gives 3, and return that value back into the main function. When the function finishes, a, b, and avg are destroyed because they exist only inside the functions. Back in main, the result 3 is stored in a and s, and that's what gets printed as the final output. So here, the key takeaway, in passed by value, the functions receive a copy of the data, not the actual variable. That's why any change inside the function doesn't affect the original values.
So why rather using pointer? Well, pointers let us do the thing that normal variable can't. First, they allow us to pass data by reference to functions. That means functions can change the original variable directly. Second, pointers let us manage memory dynamically, use functions like malloc and free. And finally, pointers are what make complex structures like linked list and tree possible. Without pointers, C would be another boring language.
Now, let's see why pointers are so useful, especially when used inside a function. Here, we have a simple example called swapchar. It takes two character pointers A and B and swaps the value that they point to. We'll go through its function step by step to see what's really happening in memory. In the main function, let's start from line 12. We declare two variables, char c1 equal A, char c2 equal B. So now, c1 stores the character A and c2 stores B. Each one had its own memory location. For example, c1 might be addressed 1000 or 1000, and c2 at address 1001. You can see that in the table c1 equal A, c2 equal B, both create at line 12. Next, at line 13, we call the function swapchar ampersand c1 and ampersand c2. Notice that we are not passing the value A and B. We are passing the addresses using the ampersand operator. That means inside the function, A will point to the address of C1 and B will point to the address of C2. So now, the function can directly modify the original variables in memory. This concept is called passing by reference. Now, at line 2, the function definition reads this. This means both A and B are pointers to characters. After the function is called, A holds the address of C1 and points to character A, while B holds the address of C2 and points to character B. This is why any changes we make through A or B will affect the actual variables in main. At line 5, we start the swapping process. This means we take the value stored at the memory location that A points to, which is character A from C1, and store it inside a temporary variable called temp. So now, temp holds character A, and the table shows this new variable created on line 5. Next, at line 6, we write this. This tells the program to take the value pointed to by B, which is character B, and assign it to the location that A points to. In other words, we just change the value of C1 to character B. So now C1 or A has character B, while C2 still has character B for now. Then at line 7, we finish the swap. Here, we take the value stored in temp, which is character A, and place it into the location that B points to, which is C2. So C2 becomes character A. Now the swap is complete. C1 holds character B and C2 holds character A. Let's summarize everything we learned step by step. 1. At the start, we held C1 is character A and C2 is character B. Second, we call swapchar, passing the addresses instead of values. 3. Inside the function, pointers A and B point directly to C1 and C2. 4. The temporary variable temp stores character A. 5. The value at A is replaced by character B. 6. The value at B is replaced by character A. And just like that, without returning any value, the original variables in main are swapped successfully. This is the power of pointers and passive by reference in C. They allow a function to directly modify variables outside its own scope, something you simply can't do with normal value passing.
Now let's move on to the next topic of common mistakes that often happen when using pointers. We'll start with the first one, initialize pointers. In this example, the pointer PTR doesn't point to any valid memory yet. So when you try to assign a value to *PTR, the program doesn't know where to put that file. This can cause random memory access, caches, or collected data. The first way is to make sure your pointer points to a valid variable first. Now PTR points to the address of X, and your program works perfectly. Remember, always initialize your pointers before using them. The next common mistake is confusing between the asterisk and ampersand operator. Look at the long example. This line tries to assign the value of X to the pointer, but X is just an integer, not an address. That's why this caused an error. The correct version is, here we use ampersand X, which means the address of X. Now PTR correctly points to X, so always remember ampersand means address of, asterisk means value at. Make them up is one of the easiest way to break your program. Finally, let's look at misunderstanding in declaring multiple pointers. Here the incorrect way. It may look like both P1 and P2 are pointers, but they are not. Only P1 is a pointer to integer, while P2 is just a normal integer variable. The correct way to declare both as pointer. You need to put the asterisk before each variable name, like the example. Both P1 and P2 are now properly declared as pointers. This is a small mistake, but it can cause big confusion. So always double check your pointer declarations. So to recap 3 pointer mistakes. 1. Using uninitialized pointers. Pointer not pointing anywhere. 2. Confusing between asterisk and ampersand, mixing up value and address. Lastly, misdeclaring multiple pointers. Only some become pointers. Avoid this and you will already be much safer when working with pointers in C.
Hello everyone. Before we wrap up, let's put what we learned about C pointers into practice with a short exercise. This will help you see how all the pieces fit together. Exercise 1. Pointer dereferencing and addition. Take a look at the code on the screen. We have 2 integer variables, A and B, initialized with values, and 2 pointers, P1 and P2, pointing to them. The final line calculates the value of sum. Your task is to determine the final value stored in the variable sum. You have 1 minute to figure this out. Time starts now. Time is up. Let's check the answer. Line 1. in A equal to 5, B equal 8, and in sum. This means establish A as 5 and B as 8. Line 2. In xp1 equal to ampersand A, xp2 equal to ampersand B. Mean P1 stores the address of 5 and P2 stores the address of 8. Line 3. Sum equal to asterisk P1 plus asterisk P2. This means invokes the dereference operators asterisk. Asterisk P1 retrieves the value at the address held by P1, which is the value of A or 5. Asterisk P2 retrieves the value at the address held by P2, which is the value of B or 8. The calculation is 5 plus 8. The variable sum will be 13. Exercise 2. Pointer to a pointer or double pointer. This second problem introduces the concept of a double pointer or a pointer to a pointer. We have var, a single pointer ptr1, and a double pointer ptr2. Your goal is to determine the output of the final printf statement. Remember, you must apply the dereference operation twice to get to the final value. You have 1 minute to solve this. Time starts now. Oh, time is up. Let's look at the solution. Line 1. In var equal to 10. This initializes our base value. Line 2. ptr1 points to var. Value is 10. Line 3. ptr2 points to ptr1. This is the double in direction. Line 4. The expression is asterisk ptr2. Let's trace it. The first dereference asterisk ptr2 resolves to the value stored in ptr2, which is the address of ptr1. The second dereference asterisk ptr2 or asterisk ptr1 resolves to the value stored at the address of ptr1, which is the value of var. As shown in the slide breakdown, asterisk ptr2 to asterisk ptr2 to asterisk ptr1 and to 10. The output of the code will be 10. That concludes our quick exercise on C pointers. I hope this hands-on practice had clarified how single and double pointers work.
Let's quickly recap what we learned. A pointer is a variable that stores the address of another variable. You can use the ampersand operator to get the address of a variable, and the asterisk operator to access the value stored at that address. Pointers allow you to manipulate data directly in memory, which makes them essential for dynamic memory allocation, arrays, strings, and even passing large data structures efficiently to functions. Understanding pointers are one of the keys to mastering in C programming. In this video, help you understand pointers better. Make sure to like, share, and subscribe for more C programming tips. Thanks for watching and see you in the next one.